Okay, if you want to save yourself a little bit of hassle, I put some notes on Schoology for the problems that we're going to do today, so you don't have to copy down these big, long word problems. So if you want to take a look at that, great. If you don't, you can write them down. It's up to you. If you want to print them later, it doesn't matter. But it might save yourself a little, might save you a little bit of hassle if you have those sitting in front of you. I'm out of Kleenex. I'm sorry. I do have napkins if anybody's in nasal distress. Good there, Alex? Yeah. Uh-huh. You want to just finish that round and we wait for you, or? No, don't wait. Okay, so today we have a difficult subject, but it is our second to last subject, and the other thing is the last subject is easy. So this is our last difficult subject to learn, and it's called work. We're going to start easy and then ramp it up. And you probably have done this in physics, yes? Yeah? Well, it'll be interesting to see what approach you took in physics versus what approach we take here in math. So, we're going to calculate the work done by a constant force, okay, which means I start pushing on Olivia's desk, she slides backwards, I keep pushing, constant force. We'll talk about a variable force. Okay, so what would a variable force be? Well, I start pushing Olivia's desk and then all of a sudden we get to a hill and it changes. Okay, that's a variable force. And then of course today you should become a Jedi Master. All right, let's do the easy one first. Force times distance. You knew that, right, from physics? Yeah, obviously. When you're a physics master like Sam, forget about Jedi Master. Sam's a physics master. Force times distance, that's it. How much force did you apply over what kind of distance? All the different types of forces. We're going to think about weight as a force. That's our primary idea that we're going to use in this math class. So I know in physics you do all kinds of weird forces, things colliding with each other, things spun in circles, things pushed, pulled, dropped, all that other fun stuff. We're going to focus mainly on the idea of the weight of an object being its force. Are you all familiar with the difference between weight and mass? Explain it to me. Brennan.
Is weight the one where you have to multiply it by negative 9 point something?
So what do I weigh on the earth? What do you think I weigh, Brendan?
175.
160 maybe?
Nice. So if I go to the moon, how much will I weigh? Brendan? More or less?
Less.
It'll change, right? Yeah, gravity changes, my weight changes. What's my mass here?
That's how much
180 divided by 2.2 kilograms. Kilograms is mass, right? Okay. Now, if I go to the moon, what's my mass going to be? The same, right? It doesn't change. Okay. So, weight is actually force. It's the force of gravity on a mass. Mass never changes. Doesn't matter where you take me in the universe, my mass will be the same. My weight will change. If I go to low gravity, my weight is less. If I go to high gravity, my weight is more. The amount of force that you're pushing down. We're all good with that concept, right? Okay, beautiful. Yes?
Is it always, it's going to be force times distance, not displacement?
I seldomly, if ever, like to use words like never and always.
Do we, alright,
You got that, right?
yeah,
Thanks. What?
I got it, right?
No, I wasn't talking to you. Right.
Yes.
Good?
Good.
That interaction made no sense whatsoever. How much work is done pushing a 50-pound object 4 feet? $200, done.
200 works.
Any problems there? Okay, good. Constant force. Take a weight, I pick it up. I'm doing a constant work, and that's just simply multiplication. Foot-pounds, or pound-feet if you'd like, it doesn't matter. There are some weird units when we get to work. And again, not very exciting. Let's change it. John, give an example of a situation that would use a variable force other than ones we've already discussed, like pushing Olivia up a hill.
A tornado,
How so?
wind, the force by wind changes.
Yeah. You can assume that a tornado, when it plows through an area, the speed that it spins, the force that it generates is not constant. It changes over time. Okay, good. Any other ideas? Of course, Cam.
If you're pushing Olivia and then you decide to push with less force, or if there's friction,
Well, wouldn't there be friction?
not necessarily.
How would you eliminate friction?
Use
Here in space.
frictionless physics eyes, as Mr. Grassi would say.
But there's no such thing.
Space.
In
The final frontier?
Don't you assume
We'll change the amount of friction.
Okay, but still friction, right? But you can reduce the amount of friction
Yeah.
by putting you on a chair on a giant air hockey table and sliding you around. Which Why hasn't anybody created a ride where you actually ride the air hockey puck all over them?
Like a
Disneyland did,
giant
and then it failed. It was recently in Tomorrowland.
Okay, let's try this one then. Blah, 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 blah. So in the work problems, we're gonna use ideas that we've already used in other problems in this chapter, and we're gonna figure out the work on a little chunk of this thing that we're dealing with, and you'll see some different examples. And we're gonna calculate the work, and then we're gonna use an integral to add up all that work. So we're gonna continue to use the integral as an accumulator. Okay, find a little bit of work, use the integral to accumulate all that work, and then we're done. It varies sometimes with problems depending on how you're gonna set it up. So I have a couple different examples that I think will pretty much outline all the different types of examples you'll see. We change force times distance to be that. Work is determined by the integral from a to b of f of x dx. F of x is going to be, notice it's capital F, that's not going to be the function, that's going to be our force. We're gonna have to calculate that. Most of the time that force will be the weight of an object, or the weight of part of an object. Dx is the distance. Pretty much two ways to think about this. I'm going to calculate how much work it takes to move something a little tiny distance and then accumulate. Or I'm going to calculate how much work it takes to move a little tiny piece of it over the distance and then accumulate. Okay. Understand the difference? If I want to move a big chunk of rock, I can calculate how much it takes to move that rock just a little bit distance and then accumulate it that longer distance. Or I can take a little chunk of the rock, figure out what it takes to move that the whole distance, and then accumulate all the other chunks of the rock. Depending on the problem, we'll mandate which technique we need to use. As much as I would like to skip this because springs are boring, they do pop up more on the AP test than I would like. So Robert Hooke, that's him. Created the something that he named after himself, because that's what all scientists and mathematicians do. They come up with something clever, they name it after themselves. Hooke's law. What Hooke's law does is it allows you to calculate the force for a spring. Every spring has its own spring constant. Some springs are weaker or stiffer than other springs. A slinky is going to be less stiff than the spring on your garage door. How far does that spring stretch? How far does it not stretch? Okay, Kx, K is the spring constant. When you take that spring constant times x, that's going to give us our force used for that spring. Okay. There's some springs. 12-pound force is used to stretch a spring from its neutral length of 8 inches to 11 inches. how much work is done stretching the spring from 8 to 13 inches and 10 to 13 inches. Okay, what we don't know initially is the spring constant. You find the spring constant. Using Hooke's law, we can calculate the spring constant and apply it to all the other functions. I know that it takes 12 pounds of force to move that spring, what distance? 3 inches, 8 to 11. And therefore, the spring constant for this spring is 4. Which means that our force now becomes 4x. So regardless of how far I stretch the spring, it's going to be kx, Hooke's law, and we solve for k to be 4. How we doing so far? We good? Did I lose anybody? Abby, you okay? You just can't see.
Mhm.
Don't like the bottom of the board.
No,
My bad.
it's okay.
Somebody's melon in the way?
No.
Ella, move your melon. There you go. Problem solved.
Thank you.
Okay, put it back, Ella. Good job. Okay, part A. How far are we stretching the spring? I know the spring constant, I know the force. I have to calculate the distance. And it's pretty straightforward. We're going from 0, the neutral position of the spring. Do you understand what the neutral position of the spring is?
When it's closed.
Yeah, you just hang the spring there. With no weight on it, just how far does it hang down? Just without a weight on it. In this case, it's 8 inches. Then we stretch it down to 13, and therefore we get that. Now notice it's 0 to 5, not 8 to 13, because 8 is its neutral position. That's 0 for us. And we stretch it a distance of 5 inches, not 13. That's its final position, not distance.
When it's linear, won't it give you the same answer though?
No.
From
Think about when you stretch a spring. So you got a spring hanging from the ceiling with a weight on it. It's easy to pull it initially, but then as you get further down towards the bottom, the spring starts to resist more. So that force is changing over time.
But if you were to have the integral from 8 to 13, or yeah, 8 to 13, wouldn't that sum you the same numbers as 0 to 5?
You tell me.
Yeah.
Would it? So you take the integral of 4x, put in 13, put in 8, subtract those, you're gonna get the same number if you put in 0 and 5?
No.
No. But that will happen.
Yeah.
Some people are gonna do that mistake. Don't make that mistake. I don't know, can you do a mistake? Yeah, you can do a mistake, can't you? In case you couldn't take the antiderivative of 4x, I included it for you. 50 inch pounds, or pound inches, depending on how much, or how you want to phrase that. Sam, why would you ask a question? You're a physics master.
Yeah. What is neutral since like isn't the Earth still pulling it out?
So technically, that's what's creating the neutral position. If you take that spring and you throw it out in space, you're gonna get a different neutral position.
Oh,
You okay with that?
I didn't think of that.
Yeah. Well, that's why he's the physics
yeah.
major. Abby?
The 4 came from the previous slide, right?
Right, that's kx. This is Hooke's law.
So you just, you put the X.
Right. So remember, when we went back to the very beginning, we're doing f of x dx. This is f of x. Hooke's, in this particular case, when you're working with springs, f of x is going to be Hooke's law. Gesundheit. I forget what part B was. Part B was well, we did 8 to 13. Part B is 10 to 13. What's going to change? Shh. Gesundheit. Is that 3? Hat trick. You got a 4th?
Maybe.
Cool. Should we wait? Look up in the light. It'll help.
Don't look at the light.
No, that's don't come into the light.
Yeah.
Anybody name the movie?
SpongeBob?
Yeah, SpongeBob.
I'm
Thanks,
pretty sure
Kim.
I think it's in the SpongeBob.
It might be, but that's not where it's originally from.
I watched Sponge Out of Water for the
Here we
first
go.
time. For the first time, and
like a
people
therapy
had said that movie
When I was a little
terrible.
kid, I
It was
watched it.
amazing.
It wasn't even bad.
It was amazing. I saw it in
I could light
theaters.
you on fire. Talking.
But
Mr. Edie, have you seen Sponge Out of Water?
Yeah.
Yes.
Yeah, it wasn't
I
bad.
know Steve's talking about that. They saw where they're crying.
It doesn't.
Imagine talking about them.
When we go from 10 to 13, our neutral position is still 8. So we're starting at 2 and going to 5.
Yeah.
Everything else stays the same. Spring hasn't changed, same spring constant, different limits of integration, and therefore we get 42 inch-pounds. Which makes sense, we're stretching it a shorter distance. Brian?
Can you explain why the integral's 2 to 5?
Yeah, so I have a spring. And it's just hanging down there, that's its natural position. Okay. So instead of thinking this as 8, think of this as 0. Then I'm taking that spring and I'm stretching it down to a total distance of 13. Which really all I did is I stretched the spring to 5. Okay, so that's the first part of the problem, because I went from 8 to 13. Second part then says, oh wait a second, the spring is already stretched a little bit down here to 10. And now what kind of forces are going to take it down to 13? So that distance is, we're going from 2 down to 5. Okay? Good? Makes sense that the work would be less, because you're moving at a shorter distance. Now things get interesting. We have a cable hanging over the side of a building with a big weight attached to it. And I'm going to start lifting. I think there's a picture, right?
Yeah.
It looks scary.
The picture.
That's
but
scary.
it's- Yeah, it's like there's different shades of colors of black.
Now it became Casey's therapy hour. Anybody else need a couple minutes? It's Tuesday. Sam does need.
These were debated by existence.
As I start to pull that weight up, one thing changes, one thing doesn't change. And hopefully you recognize that the 800 pounds is not going to change. That's a constant force. Just like in the very first problem we did, force times distance. However, the weight of the cable will change because I'll have less cable there. Does that make sense?
I think we need a free body diagram.
Sam.
Do you know how to solve the 3-body problem?
Maybe, but I want to see you do it first.
Oh.
I want to make sure you
He
got
wants
it.
to see that
You can do it.
Yeah, Mr. Edie.
I mean, I can show you,
He
but
needs-
that's a good teaching technique. If you don't know, just ask them, right? So how do we do this problem? So it works great. So, yeah, I could, but let's see you do it first. Can you jump out of that 3rd-story window and walk away unscathed? Yeah, but can you? Okay, so that's what I already said. That changes, blah, 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 blah. So first things first, I'm going to calculate the total weight of the cable hanging off the side of the building. Actually, I didn't because it gave it to me. I just kidding. 150-pound cable, 50 feet of it hanging off the edge of the building. I know that it's 3 pounds per foot. And you can change that unit to be whatever you want, but that seems to be a good idea there because we're working with pounds and feet, so we want pounds per foot. As I pull the cable up, the total weight goes down, but this ratio will stay the same. Okay. So the question is, how do I set up this integral? Well, we're still going back to the idea of force times distance. What I need to calculate is the weight of the scenario at any given point in time, and I don't really need to calculate the distance. You'll see why in a second. So what doesn't change is that 800 pounds. It doesn't matter if I just start lifting it or I'm almost close to the top, the 800 pounds stays the same. I'm starting with 150 pounds of cable. And as I start to pull in that cable, things will change. For instance, if I pull in X feet of cable, the 150 pounds will decrease. Are you with me? By how much? Okay? No, that's kilograms. Why?
Because 2/5 of the cable is being pulled up.
But you don't know how much of the cable I pulled up.
I thought it was 20 feet.
Eventually it will be, but initially I just wanna say, if I pull up a little bit, how much does the weight of the cable change? Let's suppose I pull up a foot. How much does the cable weigh? Or I shouldn't say it. If I pull up a foot, how much cable, what's the weight of the cable remaining hanging over the edge of the building? How much?
3 pounds less.
Which is?
147.
147, beautiful. I pull up 2 feet. What's the cable weigh? 144. I pull up 10 feet. 120, excellent. Are we seeing a pattern here? Kev, I pull up X feet. How much does the cable weigh? Casey?
150 minus 3x.
Good.
Boom shakalaka.
You wanna explain that? I think I have it here, hold on.
Sam?
Yeah.
I could, but
So,
I'll
yes,
let
sir.
you do it.
Casey had that before you.
Oh, you're cheating.
No,
You do it.
I wrote it down.
Oh, did you?
Yeah.
Good.
Sam had it too.
Of course he did, I didn't even bother to ask Sam.
Sam wrote
I
this
know
problem.
he knew it.
Sam wrote this
Sam,
problem.
Sam can barely stay awake, he's so bored right now. You already have the answer, don't you, Sam?
Maybe.
Why don't you
Oh,
show
do
us?
you have the answer, Mr. Reedy?
Yeah.
I didn't
Why,
send you
yeah,
the
why don't you tell me what the answer?
Oh, boy.
The real test is.
Okay, so this is the weight at any given point in time. So if we start X is 0, I haven't pulled any cable in and it weighs 150 pounds. If I pull in 10 feet of cable, I've got 120 pounds plus the 800, that never changes. How does this become work? Well, we have to take the force, which is the weight, and multiply it by the distance. So here's what we're gonna do that, I don't know if you did this in physics, but we're just gonna calculate what it takes to move this a very, very short distance. And if it moves a very, very short distance, how do we express that in calculus? Dx, correct. This first part is our force. That's the weight of the scenario at any given point in time. Dx is how far we're going to move it. How far are we going to move it? A little bit. And then we're going to take all those little bitty movements from 0 to 20. So this is the limit of integration that comes from, I don't have the original problem here, but it says you pull up 20 feet of cable. Okay, so again, we're breaking it down into calculating the work to do a little bit of work, and then integrating it to add up all those little bitty pieces of work. Easy integral, yes? Do we need to bother with that?
No.
Good. There's the weight. There's the small distance. Integrate. Dun, 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 dun. 18,400 foot-pounds.
It's gonna be fun with those.
Fun words. Let me say it again. Foot-pounds. Is there any reason why you just repeated that, Cam? You just wanted to say foot-pounds?
Yeah, it's a funny word. Like pound feet.
Or
Taking
like,
it too far.
Uh-oh.
Sam.
Don't be disparaging the physics world. Sam will be angry. All right, any problems? Beautiful. Let's change it a little bit.
I'm just gonna start floating around because Sam's gonna turn off.
Instead of calculating the work to move the whole scenario and then integrating it for the whole distance, we're going to look at a different option. And the different option is we're going to calculate the work to move a little piece of it and then integrate it to get all the pieces together. A conical tank. By the way, conical tanks look like ice cream cones, not upside down. Nobody stores something in an upside down cone. Except
salt.
road salt.
Salt, yeah.
Road salt, yeah. But that isn't really a tank, that's a shelter. A conical tank has an altitude of 20 and a radius of 4. How much work is done pumping the water over the top of the edge of the tank is empty. Water has, density. We're gonna need that in a second. There's our picture. Well, that looks familiar. That looks like a related rates problem. It's not, relax.
It's about to have a heart attack.
What I have there is a little sliver of water. I'm going to calculate the work to move that little sliver of water, and then I'm going to integrate all those little slivers of water. Correct. What's the volume of that sliver of water, Taylor? Don't look at me in that tone of voice. Come over there and knock you into tomorrow.
I don't know.
What shape is that sliver of water?
Circle. Cone. What?
It's not a circle.
Oh, it's a disc.
It's a disc. What's the volume of a disc?
Oh. It's V equals pi times integral
Oh,
a.
no. Not like a calculus student. Just like a geometry student. What's the volume of that disc? What's the geometric term that my sophomores would know? No, they're freshmen. I don't know. Whatever those kids are. What would they call that thing? They wouldn't call it a disc. They don't know that word.
Cylinder.
They'd call it a cylinder. Correct. So what's the volume of that cylinder?
Isn't it like pi r squared times h?
Perfect.
Or something?
Good. Okay, now we switch back into calculus mode. We don't want h, because I want a small sliver. So instead of h, what are we gonna call it?
X. dx.
dx, good. Radius is still the same. Pi is still the same, that hasn't changed. Okay. Everybody good? Find the volume of this sliver of water. By the way, it won't always be water. That's where this will come into play in a second. Why do I care about the density? Maybe physics, maybe chemistry. Where does density come into this scenario?
I've got the
Shh. I'm sure you do.
His dad's a chemist.
Well, that doesn't mean anything.
Oh no. You wouldn't even begin to know.
Well, that's Olivia, what does your dad do for a living?
He used to be my gym teacher.
Yeah.
He's a what?
He's a gym teacher at Lincoln.
Do you know anything about teaching gym? No. Sam, what's your dad do for a living?
He's a lawyer.
He's a lawyer. You know anything about law?
No.
No, there you go. So
It
why
comes
would
up
we
at the-
assume that just because your dad's a chemist?
It comes up at the dinner table every night.
You live in an abusive household?
No, I just love learning about research.
Like before you can eat, they ask you the atomic weight of
Yeah.
some element of the what is that thing called?
Periodic table of
I almost said
elements.
table of contents. Periodic table. You can see how much I love chemistry.
Who do you think would score better if you were to take our chem test or if Teresa were to take our calc test?
Teresa teaches algebra.
You mean I take a chem test?
Yeah.
Guaranteed Teresa would score better on the calc test.
He teaches it.
I can barely spell chemistry.
Can I explain the density of the water?
His dad's kind of in case you could ask.
I'm opposed to this endeavor, but my friend Dennis has suggested that maybe this would be
Meaningful
a
exercise.
route that we would want to pursue. So, all right, go ahead.
Okay, so density of a liquid or anything is mass over its volume. So if something has a density of 1 gram per centimeter, that means there's 1 gram per cubic centimeter of volume that you can fill up. So if you were to have 20 grams per centimeter, it would weigh 20 times more in a cubic centimeter than the 1 gram per centimeter cube. So if you have water that weighs 1 gram per centimeter cubed, then you have oil, there's going to be a different amount of oil in there.
How does that apply to what we're doing?
That was a good explanation.
I mean, that's,
It's good density discussion.
yeah, it's good density discussion, so.
You didn't say it, Ron, you said it.
He just took the opportunity and ran with that, right?
So if it's a different substance, then it's gonna have different amounts of work done because it's different amounts of mass being acted on.
How is work defined?
Force times mass. Or displacement.
Times distance.
Force times.
And for our purposes, force is defined as weight, correct? Well, Taylor just helped us figure out the volume of that disk. The volume is not the weight. And so we can use the density with the volume to come up with the weight of that sliver. You'll notice in the picture, I chose a disk somewhere on that cone. It doesn't matter where you choose it, it's a random distance. But I have to pump that disk of water over the top of the tank, which is that distance x. The problems get a little bizarre because you can choose how to define things. In other words, I chose the distance I have to pump this disk as being x. That means it's 20 minus x from the bottom of the tank. You could do it the other way around. It's x units away from the bottom of the tank, therefore I have to pump it 20 minus x. The answers are the same, the work is a little bit different, no pun intended. We know the volume of this already, pi r squared times dx. We take the volume and the density to get the weight. So Ken, you said, what's the relationship between volume, density, and
Density.
weight?
Density
And
is
mass.
mass over volume, so volume times density equals mass.
Volume times density equals mass, and for our purposes, mass and weight are the same thing. Okay, so, blah, 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 we talked about that already, and so we get this guy. You do not need to memorize the density of water,
1 gram per cubic centimeter.
or 62.4 pounds per cubic foot.
Yeah.
Thanks, nerd.
Specific heat's 4.
You teach math first.
We answered that question already, we're gonna pump that x, and we get that bad boy. Now, let's explain the parts of this guy. What's that? Whoops, not the x. Stopping there. What does that represent? The weight of the sliver. The x is the distance. And you'll notice that's why the dx isn't on the back end. I purposely left it in there so we could group that whole weight thing together. Weight times distance is what we're looking for, force times distance, that's the work. And we want to pump slivers of water from 0 to 20. In other words, in that tank, where am I taking slivers from? Or where can I put that sliver of water when I'm setting up the problem? I can put it anywhere from 0 to 20. Now, how do you change the problem? Well, we could say, how much work does it take to empty half of the tank? Change your limits of integration. We could change the material that we're pumping out. Maybe it's rocket fuel, different density. Maybe it's crappy suns. There's a good problem. How much work is required to empty a crappy sun thing? What are those things, envelopes? Pouches?
Yeah, they're like pouches.
Use pouches, I believe.
Yeah. I feel like the volume of those would be pretty difficult to find.
They're just pouches, I believe it says on the box.
Does it say?
Pouches.
Yeah.
Pouches.
Why do you wear sunglasses?
It's got the volume of each pouch.
Really?
Anybody know the density of Crappy Sun's lemonade?
I think it would,
I'd guess around the same as water.
no, they're really sour, so.
62.4.
If not a little more. 1.1 grams per
Make your crap up now, aren't you?
1.1 grams per centimeter cube is what I'm guessing. We'll see.
Alrighty.
87.
Get rid of this. What's wrong with this?
Yeah, we don't want
2 variables, that's bad. Vice, Mr. Trinkle.
Hey,
Trinkle.
Hi, everybody.
Okay, let's stop ripping on chemistry now.
Where's your desk?
I've had my desk for months.
Yeah.
Also, they took it away. I tried to hit Sam with it. You know my friend Sam? Physics master.
Physics math.
What are we working on?
We're calculating the amount of work to empty a cone full of agua. That's Spanish for water.
Oh, I didn't understand that. Thank you.
All right, you're all fairly bright. Do I want to get rid of the x or do I want to get rid of the r?
DR.
Why, Casey?
Because you have DX already.
Yeah. Otherwise, r is just a constant. And r can't be a constant because r is going to change depending on where we put that. How do we get rid of r? This will go back to our related rates days.
Mr. Edie, there's over like 50 flavors of Capri Suns.
That's an idiot. He's like the Rain Man of Capri Sun. Yeah, 50 flavors. I can name them all.
No, there's so many.
Strawberry
There's like
kiwi.
multivitamin Capri Sun.
You must have talking about Desmond, I believe, Mr. Pringle.
Drinks, what happened this weekend? No effort.
What?
I figured as much.
Do you know what the pirate's favorite letter is?
R.
No, matey. My first love be the sea.
Why does it? I have a hard song with
What happened?
You sent years
You just look like you're in pain from that.
I'm embarrassed I played into that. Hey, similar triangles. Oh, quit your whining. How long is that?
25,
And this? And this whole distance?
26.
20? And this? Oh yeah, similar triangle. Come on now. Height of the small triangle over the base of the small triangle equals the height of the big triangle over the base of the big triangle. And since you already told me we want to get rid of r, I solve for r, plug that in.
I remember those, Mr.
Once again, thank you for sharing, Cam.
You did a good job.
How we doing? Take everything that's a constant, the 62.4 in the pie, and move it out in front so you don't have to deal with it.
Pi pound feet.
That's kind of a big jump. I FN into it. 33,280 pi foot-pounds, or pound-foots.
Or pi pound feet.
If we change the liquid, the density will change. Let's suppose we put syrup in there. Maybe a high-quality maple syrup. Will it take more or less work to empty the tank? Mary? More. Why?
Because it's thicker, or it has more density.
Good. Density goes up. Cam? What has a lower density than water?
Air.
What liquid has a lower density than water?
Very few. I think peroxide does.
Okay.
So
Hydrogen peroxide?
Yeah, hydrogen peroxide.
Okay. H2O2?
Mercury does, I was gonna say, has a lower density.
Then water?
I think so.
Oh, I don't know if I believe that.
Or is it the other way around?
Wait.
That's
Let's get some mercury and let
That's
Cam play
literally
with it. It's fun to chase some little balls all over.
Yeah,
the place.
same with lead paint. I did.
You ever tasted mercury?
No, I don't really eat fish, but when I found out that tuna had mercury in it, I'm like,
All
no, but tuna's just extremely
Really?
toxic food a lot.
I want.
Relax.
There are some types of mercury that are not.
No, we have.
We're done.